Dr. Zampo. Welcome to our maths tutorial programme. So earlier, when I told you that area was only applicable to 2D shapes, shapes with 2 dimensions, or flat shapes like a piece of paper, that wasn't strictly true. You can look at the area of a 3D shape by examining the area on the outside of the 3D shape, looking at each face individually. This is called looking at surface area of a 3D shape. The way that we do this is we need to flatten this 3D shape by cutting out each of the individual faces. If we take our 3D shape and open it out, like that, we have made what's called a net. A net is an unfolded 3D shape. A net can be folded back up to make the 3D shape that we originally started with. So now we're really getting into surface area. So when we look at this shape, we have got duplicates of faces. If we look at this face here, this portion here, you can see we've actually got 2 of those faces. We have one here, and we have one here as well. And I've made a representation of that on the whiteboard. So quickly, let's measure these faces. We know that they're rectangles. So we've got 18 centimetres by 31 centimetres. So 18 centimetres by 31 centimetres. And for the next face we're going to look at is this face here, the long thin one that makes up the sides of our box. So we've got 2 of those faces. Let's measure this. 9 centimetres, and it should be the same length as the other one, 31 centimetres. So this is the long face. We've got 9 centimetres and again 31 centimetres. And finally, let's have a look at the face that makes up the top and bottom of our box, which is this face here. And this one should have the same width as the first rectangle, which is 18 centimetres, and it has a height of 9 centimetres. So they all tie together. So we've got 9 centimetres and 18 centimetres. So now we have our 3 faces, of course remembering that we actually have 2 of this face in our net, 2 of that face in our net, and 2 of that face in our net. So now that we have our dimensions, we can work out the area of each of the faces and then combine them to find a total surface area for our cardboard box. So let's start off. We know that the area of a rectangle is the base measurement times the height measurement. So for this first rectangle, we have a calculation of 18 times 31, which gives us 558 centimetres squared. But we know that we have 2 of those faces. So I need to multiply my answer by 2, and that gives me a grand total of 1,116 centimetres squared. That is for these 2 faces, the area for these 2 faces. So let's now have a look at the face that makes up the top and the bottom of the box. So the first thing that I need to do, base times height, to work out what the area is for one of those faces. And that gives me 162 centimetres squared. And then remembering that I have 2 of those faces, I have a top and a bottom, so I need to multiply my answer by 2. And I get a total of 324 centimetres squared for both of those 2 faces. So finally, we're going to have a look at the side face. If you remember, this long, thin face is the face that makes up the side of our box. So to do this, we need to calculate 9 multiplied by 31, and we received 279 centimetres squared. Remembering that we have 2 faces because we have 2 sides, so we need to multiply our answer by 2, and we receive 558 centimetres squared total area for those 2 faces. So finally then, to work out my total surface area, all I need to do is combine all of those areas that I've just found out. So total and combine means that the operation we're looking for is add them together. So I now need to add together all 3 of the total areas I've found in the boxes. So if we add 1,116, 324, and 558 centimetres, we will find that we have got a total surface area for this cardboard box of 1,998 centimetres squared. So if you can imagine how big a centimetre square will look like, a square with 1 centimetre for each of its dimensions, we need 1,998 of them put together to make our cardboard box. And from that net, we can then fold it back up again and put it back into our 3D shape. We now understand fully surface area and how that works, but we've only really applied that to more simple examples. We're going to have a look at quite a complicated example of finding a surface area. And the most complicated example really that we're going to come across is finding the surface area of a cylinder. And we are going to use an example of finding the surface area of a prayer wheel to do this. So let's start off by looking at our cylinder. I've got a model here. The first thing to fully understand is what the net of this cylinder actually looks like. So if we were to open this cylinder up, we've got a circle at the top, we've got another circle at the bottom, and if we were to make a cut down the end of this cylinder and open it up, we would see that we in fact have a rectangle. So a cylinder is actually made up of a rectangle, circle for the top, and a circle for the bottom. The most complicated bit to understand there is this curved portion and how it can go from being a cylindrical curved shape to opening it up for the net to make a rectangle. When we know that we've got these 3 shapes that make up our cylinder, we can very easily start to calculate our surface area. But there are a few more things that we need to take into account before we can do this. So the first thing that we need to work out is what the dimensions of our rectangle might be. So let's have a look, shall we? I'm going to fold this cardboard back up. The actual height or length of the cylinder will make up this portion of our rectangle. So let's remember that. It's the bit that the sellotape is on. So I'm going to unfold that, and the height of my cylinder makes up this dimension here. So let's label that on. That's the height of our cylinder. So to find out the area of this rectangle, remember we're looking at surface area here, I still need to find out this dimension. Remember, it's a 2D shape. To find out area, I need to have 2 dimensions. So let's have a look again, shall we? I'm going to fold this back up again. Let's see if we can work it out. At the top of my cylinder, I have a circle. And the actual dimension that I need is the distance that goes all the way around a circle. Have a look at that. The distance that goes all the way around the circle, if I open it up that is the dimension of this portion here. So there is a name that we give this dimension, the distance that is all the way around the circle, and that is called circumference. And to find the circumference of a circle, we have a formula, which we can see here. The circumference of a circle is pi times the diameter being the distance all the way across the middle of the circle. The dimension across the top here is now going to be our circumference. Remember, it's the curved portion flattened out, the distance around the outside of the circle, and that is going to be pi times the diameter. I'm just going to pause for a second and talk a little bit about what the number pi actually means. Pi is a number in maths that we refer to, and it is often related to circles. Pi is a number that is irrational, which means that the decimal goes on and on and on. And pi is somewhere in the vicinity of 3.14, but there are a number of other decimal places. In fact, it never stops. Now, it's very, very difficult to remember very long numbers with many decimal places. And in maths, so that we do not have to do this, we just give this special number a name. And the name we give to it is pi. So that just explains what you can see there in the formula we're looking at for circles. So we now know that the area of our curved portion of our cylinder is the height times pi d. And then we've got two circles, and we need to find the area of each of these circle pieces. So to find the area of a circle, we know that the formula is pi r squared, where r is the radius of the circle, which is the distance from the midpoint out to the circumference. So we know that each of these has an area that is pi times the radius squared, and we have two of those. And we've said that this one, the area is going to be the height times pi times the diameter. So if we were to work out these three areas and add them together, that would give us the total surface area for our cylinder. Now, we're going to look at a real example of this, and we are going to relate what we have just learnt to finding the surface area of the prayer wheels. The prayer wheel that we're going to use for an example is the prayer wheels down at Memorial Chawton. Now, we have just been down there and we've taken some measurements. And if you can imagine that I've taken the prayer wheel and I've laid it on its side, the prayer wheels down at Memorial Chawton have a diameter of 1 metre. So across the base of the prayer wheel, the dimension is 1 metre. And they have a height of 2 metres. So here we have enough information to be able to work out the surface area of our prayer wheel. And in doing so, we can work out how much metal is physically required to make that prayer wheel. So first of all, I'm going to work out the surface area of the two circular parts of the prayer wheel that make the bottom and the top. So let's do that first. So we've got two circles and they are identical and they form the top and the bottom of the prayer wheel. And remember we said that to find the area of a circle, it's this number pi times the radius squared. This is where you need to take care, because this formula for area is asking for the radius and not the diameter. Remember, the radius is halfway across the middle and not all the way. So pi r squared. So the dimension halfway across the middle of the base and top of our prayer wheel will be 0.5 metres, half of the diameter. So this will be pi times 0.5. squared. So that will be the area for one of the bases of the prayer wheel. So let's do that on the calculator. So I'm going to do 0.5 squared first. And then I'm going to multiply my answer by pi. And the answer that I get for one area, remember, is 0.785 to 3 decimal places. And remember, we're working in metres, and it's an area, so metres squared. That's one circle, so either the base or the top. So let's work out what the area of both of them will be. So I've got 2 circles in my surface area, so I'll multiply that by 2. And the area that I have for both of them is 1.57 metres squared. So that is the area for both the top and the bottom of the prayer wheel. Now let's have a look at the curved portion. Remember that we said that the curved portion became a rectangle and that the area of the curved portion was pi times diameter times the height. So let's have a look at that. The height of, let's just draw that for you, pi times diameter times height. So the height of my prayer wheel is 2 metres times by pi, and the diameter of my prayer wheel is 1 metre. 2 times pi times 1, and the answer is 6.283 metres squared. So that's the area of the curved portion of the prayer wheel. So now to find the total surface area for the prayer wheel, I can add up the curved portion, which flattens out to become a rectangle, and the 2 circles to get a total. So I'm adding up these 2 values here. So 6.283 plus 1.57, and the total surface area, that's right over here, the total surface area for the prayer wheels at the Memorial Chawton is 7.85 to 2 decimal places metres squared. So, as we imagined earlier, if you can imagine a sheet of metal in front of you that is 1 metre by 1 metre, so a sheet of metal in front of you 1 metre by 1 metre, you would need 7, nearly 8 of those square metres to make the prayer wheels. Okay, so let's try and put that into context a little bit, because 7.85 metres squared is quite a lot of metal required to make those prayer wheels. Now let's imagine for a second and think about how many prayer wheels there may be that exist in Bhutan today. So let's take a conservative estimate, and let's say there are approximately 100,000 prayer wheels in Bhutan. Very conservative estimate. Now let's have a look at this number and let's think, well, that's actually quite a large prayer wheels. Prayer wheels come in all different sizes. So let's take an average of the larger and the smaller, and let's say our average area is going to be about 4 metres squared, and we're estimating that there are approximately 100,000 in Bhutan. That means that if we were to take every single prayer wheel in Bhutan and lay them all out next to each other, as we have done here with my model cylinder, we would find that we had a total surface area of prayer wheel in Bhutan of 400,000 metres squared. Now that's a difficult number to think about. So let's try and put that into context with something that we do know about. Well, we can easily picture a football pitch. Now, football pitches are roughly 100 metres by 65 metres. So base times height, we know that the area of a football pitch is somewhere in the region of 6,500 metres squared. Now, If we were to lay all of the prayer wheels out that we've estimated that there are in Bhutan over football pitches, if I take this area and divide by the area for one football pitch, you'll find that you get approximately 62 football pitches. So if we were to take every prayer wheel in Bhutan that we have estimated exists and to lay them out, we would find that we would cover approximately 62 football pitches. That's a large area. We have looked at a number of different shapes, and we now know how to find the area of all of these shapes. We developed on that maths further to look then at surface area, and we learnt all about what a net would look like when you take a 3D shape and you fold it out to make a series of 2D shapes that we can then calculate the area of. And finally, as our super challenge, we looked at calculating the surface area of a cylinder. And to do this, we had to learn and revise skills such as finding the area of a circle, finding the circumference of a circle, and then working out what the net of a cylinder would look like, and finally calculating the surface area. An awful lot that we've been through in today's programme.